recording this in that case.
Okay. So just to outline the agenda for today, we are going to review the current machine learning modeling that we are doing and review the data and maybe some issues that we have in this perspective. So we could then share it with epidemiologists potentially and get their feedback on our methodology and approach, and maybe they will join us to help us to construct this wonderful research. Thank you, Isaac. Yeah, we can start reviewing. I assume that you keep all that in GitHub, right?
Yeah. All the code's in GitHub. So, yeah, I will share the screen.
Are you using the Jupyter notebooks just to run the Python codes eventually?
Yeah, some of that's that. Okay. Can you see my screen now?
Yep.
Okay, so, okay. So you can see me like I'm changing windows right now. I'm just trying to share a specific window, so I want to make sure it's the right one.
Sure.
Okay, so you can see like this flood forecast and this other stuff.
Yep.
Okay, so right now for modeling, there are a couple different models we've been looking at. The one we're using primarily right now is actually this multi-head attention model, though we're running it through the notebooks. This is kind of a fairly simple model that actually uses, yeah, I guess I won't go into too much detail about this because it's complex, but there was an idea of using an attention mechanism which like would take a sequence and attend to the specific parts of the sequence and find the most relevant features in that sequence. It was first used actually in neural machine translation, but a lot of other people found its utility in time series forecasting as well. So some of my long-term machine learning research has been looked at applying multi-head attention and kind of various attention mechanisms to forecast in multivariate time series. Yeah, and feel free to ask questions if you have any, because this is a lot of stuff I'm going over.
Yeah, sure. This looks familiar to me, except that I have never run the PyTorch and TensorFlow type of models. I see that code present here, but I mean, at least I'm very familiar with the general, kind of approach to construct the models and the code in Python. So as far as as long as I would understand the actual kind of like what this thing is doing, that will be enough for me to kind of get through it. Yeah.
Yeah, so that's kind of the gist of it. So basically here, just very simply, we have an initial layer which takes a certain number of input time series. We map it to a certain dimensional vector. Then we use this to encode the position. Then we run it through that attention mechanism I was talking about. Then we do a final linear layer, which kind of returns it back to the 1D output, which in this case, since we're forecasting new cases, then this should return the number of new cases, and this should return. We do have a variable forecast length, so we can try to train the model initially to forecast n number of days or 1. So that's what this final like layer is doing. But that's kind of the overview of this model.
And which variables do we have here present?
So currently, this is just the class for the model. Where we actually pass in the variables is in another part of the code. But initially, so our first training rounds, and you can see this on the weights and biases stuff, we were only, we were in essence just passing in the number of new cases from the previous days, and then for the number of, and then like other factors like day of the week. more recently we've started adding like, and we can see this in the configuration files. So these are the different parameters that are being passed now. So
Right. New cases, month, weekday, mobility, grocery, pharmacy, mobility parks. Okay. And where is this mobility data coming from? What's like the source of it?
So this current mobility data is from Google. So
Okay.
Google has been putting out, yeah, this Google mobility data and daily reports, and they have actually been doing it. A while ago, it was only at the state level, but the more recent ones have had it at the county level, which is good because that's what we've been trying to forecast at. So
Oh, fantastic. And they have this CSV documentation here, so it's pretty easy to extract and then work with it. Yeah.
yeah.
So if we would, kind of like try to shape up, what kind of analytics are we using here? What exact types of models are being applied?
Okay, I mean, so the that model was what I showed you was basically what the actual model is that is running right now.
Hmm.
We are looking at other types of models too that potentially integrates. Now I lost my previous screen, but it potentially integrates the attention cross-dimensionally too, so it would select the best feature time series. And there are lots of different complex machine learning approaches we could draw in. But at the moment, as I said, we're mainly using this kind of basic model. But some of the problems that I was saying is in general, deep learning in particular requires a lot of training data. So typically, I think
Yeah.
we would like be trying to train on, well, we want at least 1,000 or 2,000 different time steps to even begin to train well, and ideally from a whole, like in time series case from a whole period, like say like a whole year, which would get in all the various seasonal variants for forecasting. So it's been hard because we're limited on time series data. Um, one of the areas that I've done machine learning research in, though, and our basic idea was to try something called transfer learning too. So actually, what some of our previous experiments and what I wrote up in the initial abstract was actually to take this model and instead of just pre-train it on a single county, we would actually pre-train it on other counties and then like fine tune it to a specific county. So then we'd actually at least have the benefit of the model already kind of learning how the disease works on other counties. And those models did seem to perform a bit better. I you and yeah, so and the way that that was visualized was like, I guess those experiments there was a weight path because what we did is we trained it on those other things, saved the file, then reloaded it. So any of those, I think they were based on that like weight path. So yeah, so for here, like this was one of the ones we used transfer learning on, and this was these actual cases in like orange versus the predicted cases over a 10-day period in April. And yeah, it didn't fit it perfectly, but it still was a lot better than when we didn't do the transfer learning technique.
Wow, this looks very impressive in terms of it's fairly complex, and I would say that at least from my perspective, this is very new for public health interventions analytics. At least I didn't see many. I've seen some articles, yes, they exist, but it's not like just like a whole trend of doing this type of analysis. So yeah, we might have to quite get on speed with this as well. So yeah, where do we stand as of now? What are current needs, and what are the next steps? Maybe in terms of what kind of data we might need. That's my question, the first one, and then uh, maybe we can also introduce a little bit like the overview of our team, how many people we have, and what kind of skill set they have as well, just to make sure that we properly present ourselves.
Yeah, so right now, the big thing is we started to incorporate some of the mobility data. As you see, this was actually just done on the new cases and other new cases and day of the week and those basic parameters. And so far, like part of the problem is I think because even though the mobility data should help the model, it's actually adding a degree of complexity. So some of our results in purely evaluation metric terms since adding the mobility data um, actually haven't been as good. And there are a couple of reasons for that. I think because it's like essentially we're essentially making the feature vector to this model high dimensional, more high dimensional, and why that's good. It's still very limited in terms of timestamps and learning, so it's having trouble. We haven't tried that same transfer learning approach though, so I'm hoping that will increase the mobility data's performance. Um, but I guess from a modeling perspective too, what we're looking at right now is really trying to find an architecture that's very good at that transfer of knowledge. And so the idea is we'll pre-train it on like other time series data that might be entirely unrelated, like solar or wind forecasting. The idea is just that with that, the model will get a very good initialization and get very good at extracting general temporal patterns. And then we'll tune it to the specific thing, which is the COVID-19 forecasting. But where something could help and more definitely more expert knowledge help, there's always like negative transfer. So there could be like things where it learns not generally applicable temporal patterns. So if we could get like other temporal data on similar diseases, specifically like SARS and stuff, and pre-train the model on that, then it would probably learn. I think we'd have more positive transfer and a more better performance overall. So I think that's definitely one of the things we should look at.
Okay.
Like, does that make sense or?
Yeah, absolutely. I think that makes sense. I mean, the other diseases, that's probably the best type of data we should be looking for in terms of training this model properly, because that would be purely epidemiological kind of like perspective. And I think it might have a little bit more sense than, let's say, solar data or something like that, because there is no clear conclusions if that thing is even influencing the whole pandemic. So yeah, but I got the point.
Yeah. Well, yeah, and again, it's not really too like I guess the other data isn't necessarily to say something specific about the pandemic. The idea with that is just that the model, like almost with deep learning, like I guess it's like you're trying to also teach the model how to learn to learn. There's like so many like this model isn't that complex, but if we add, for instance, more layers, then the first couple layers of the model would act almost as general feature extractors. And so over time, those layers would just kind of learn and be fine tuned to just extracting general temporal patterns from any time series is the idea. Then further down the model, we get more and more task specific layers. So we start to see model layers that almost specialize in like the exact like temporal dynamics of the specific disease we're modeling. So that was the only point of the general transfer learning thing is just that hierarchical fashion in which neural networks learn. But yeah, definitely the closer data we can get to the actual pandemic, the more overall positive transfer I think we should see. So
Got it.
and another possible thing we could do is I know that you guys in epidemiology actually use SEER models a lot or basically simulations, right?
Yeah, that happens. I never done it myself, but we can find several publications to look at that and just. Um, so you think it's somehow similar to this?
Not similar to what we're doing, but actually, if we could like take simulated or synthetic data, even if it isn't real data, that could be another thing we could potentially train on. So we could pre-train on that and then fine tune on the real data. So that would, in essence, increase our data set size. Like people have done similar things in computer vision where they just like take images and they just like crop and rotate them and pre-train them on these different distortions. And even though there's a bit of noise added by them. Like as I said, when they then train on the final real images, usually performance is increased because even though there's synthetic data, it still helps that model like learn those patterns. So if like we create if we use one of those models, which from what I understand is that they could like generate like a simulation of almost like synthetic data or what stuff would look like over time and then fed it into this model, then I think that might like improve performance.
Okay, I'm making notes and I'll check this, of course. Okay,
So yeah, those are kind of the major modeling things. Then I mean, then the whole thing was like the evaluation perspective too, because we don't have that much data to evaluate on. So typically, like for instance, on flow forecasting, I think I said in that note, I like pick like various segments throughout the year, and then I test on those just to make sure the model actually learned how to incorporate seasonality. But right now we only have very limited data and a good chunk of that's going to training. So like even say if like our curve fits this real curve, like we don't really know like if this will generalize to like new data points over time. So it would be good if and I don't really have an answer to that, but I think we need more robust testing methods because, as I said, right now we're essentially gauging like a model's validity just on like how well it fits to like forecasting 2 weeks out based on a date. So these are how well forecast, for instance, on 10 days towards the end of April and early May. So yeah, definitely like I think looking for more thorough evaluation methods would be good.
got it. And what about our team? Like, so how many people will we have who possess these skills? And besides you, I mean, in terms of the modeling and the data analysis skills, and many, maybe some other.
So yeah, so we're so yeah, I'll just quickly run through that. So yeah, this hasn't been updated in a while, but our actual kind of team page and roster is here. We brought on a couple of our data scientists recently. Specifically people with some time series forecasting experience, some people more on natural language processing, but with a good sense of how machine learning works in general. So we have about, I'd say, 3 to 4 people really good at um, data science and machine learning and also time series forecasting. Um, Besides yeah, in addition to like myself, obviously you are primary epidemiologist or domain expert at this point. And then we are also bringing on just recently, we brought on 2 more kind of data engineers. While they're not good at modeling, they're helping create kind of robust pipelines that are getting us the most accurate data. So they're like working on synthesizing all the different data sources. So we have all that mobility data, that weather data, um, and even demographic data and different data at even the city and town level kind of synthesized together and brought into us on a daily level. So yeah, around 10 people or so in total. Yeah, basically mainly data scientists and kind of data engineers at now, but yeah, definitely be good to get more domain experts.
Sure. Yeah, I think it's fascinating that we have this group of people so skilled and well prepped for this sort of work. I think we probably should try to onboard one more senior epidemiologist to help us with certain um, aspects of this research. That's probably essential, just because where it gets it, it should be a very serious research at the end of the day. So we can try to actually publish and produce something really nice and probably hopefully even helpful to um, the public. So, and maybe we will also be able to obtain some additional data if we sort of like present us as a public health arm. You know what I mean? So, not necessarily for all of the events or engagements that you want to plan for the project and for the team, but specifically for data obtaining and maybe some communication with those crews like Facebook or someone else who might possess the data. So yeah, this is great, Isaac. This is great, and thank you for revision for review. My last question is So you were presenting all those graphs and everything. What kind of tool is that are you using? I mean, I never seen this before. I mean, I seen it in your previous presentations, I think, but I was just wondering what, yeah, this, is it free or is it
So
expensive?
yeah, right now we're using weights and biases, which is this experiment tracking tool. They're a good they are a good tool I learned about a couple of years ago at like one of the major machine learning conferences, and they help you track your different deep learning and machine learning experiments. So it's a really good tool. And yeah, so far they've been really nice to us. They are free for personal use and for um, personal projects, but they also gave us an actual team license because we were working on this cause. So they actually gave us a group license, so for free, which has been really nice. So and yeah, all these experiments are actually public. So like you can see these things are unlocked. So like anyone can go and view these different pages and these different kinds of reports we're using. Um, so yeah, that's kind of what that is.
And that's where we run all the models as well, right? So we don't use Jupyter notebooks or something. We just do all the actual development work here in this tool.
Um, no, so the models are built based on this GitHub code. To run the
Hmm.
models, we usually either so this is the base repo, which is kind of back from when I did the actual flow forecasting experiments, but it's a generalized time series forecasting framework. So this is the core model that like all the code calls. Then we have the specific task TS repo where we kind of feed in our specific parameters. So so yeah, and so we do use notebooks here a bit. So for instance, we run these on GPUs. Though you could actually run it without using the notebook too, but basically all the notebook does is you define a configuration file and log into weights and biases, and then it calls that core code. So basically it clones this repo, and then basically every notebook has a configuration file where it defines the parameters we're passing in. So here was when we were just doing new cases, month, weekday. And this is the model name. So like part of the benefit of using this framework that I developed over the last couple of years is we want to change the model. We just have to change the model name to whatever else is in that repo. All these other parameters are configurable, so we can configure how long the model forecasts just based on these parameters. And then, yeah, this is the sweep. So we're actually looking at which parameters result in the best forecast. So we're sweeping over different combinations to see which parameters causes the machine learning model to learn the best. And so, yeah, that's basically then, here's where the codes actually runs. And then but all this is kind of secondary because all this actually gets logged to weights and biases. So this is the central place where all the results are being collected. So.
Got it. Okay, that's amazing. So yeah, now we have the, essential overview of our process, and we can share it with people who might be interested to join us. Thank you, Isaac. I think we can stop recording at this point. Um,
Okay, yep, sure. Pull up.